everyone. My name is Rebecca Bickham, editor of AMP's Materials Performance Magazine. And joining me on today's podcast are two employees from Mobiltex. I have Tony DaCosta, who is VP of Engineering, and Sean Lawrence, who is Service Manager. And I asked them here today to join me to talk about lightning immunity in pipelines and the use of remote monitoring systems to evaluate potential damage. Thanks for joining me today, Tony and Sean. How are you both doing?
Oh, very well, thank you, Rebecca.
Thanks. Doing great.
Good. So the first thing I'd like to ask you both is to briefly introduce yourself to our listeners and give us an overview of your background as it relates to corrosion. Tony, I'll start with you.
Good day, everyone. As Rebecca mentioned, my name is Tony DaCosta, and I'm the VP of Engineering at Mobiltex. I head up the team that quickly and creatively transforms customer product research information into useful industry-leading products for our customers. I hold a Bachelor's of Applied Science from the University of British Columbia. My experience is in electronics engineering with a specialty in data communication systems. Over the last 29 years, I've put that knowledge to use in various specialized IoT product development efforts. That includes many of Mobiltex's current product offerings. In addition, I also hold a NACE CP1 certification.
Thanks, Tony. And you, Sean?
Hi, thanks, Rebecca. As mentioned, my name is Sean, and I'm the service manager here at Mobiltex. I work with our service team to help our clients install and operate Mobiltex products. I've worked at Mobiltex for over 20 years and have seen numerous examples of how lightning affects both pipelines and CP systems. I've worked with our clients to ensure they have robust systems and they get the data they need when they need it. I have a Bachelor of Applied Information Systems. I'm also a certified engineering technologist. And finally, I have NACE CP2 certification.
Great. Thank you both for sharing that. So my first question for you today is, what are the ways a lightning strike could affect a pipeline, and why are flashovers often more damaging than a direct lightning strike?
Great questions, Rebecca. Let's first start with some background on lightning itself. Lightning is caused by a static buildup of charge within clouds. During storms, warm air rises and moisture in that air current starts to freeze. As those ice crystals collide, a charge buildup gradually occurs. Now, normally, air is a reasonable insulator with a high breakdown strength that resists the flow of the charge accumulation. But eventually, the potential of the cloud charge relative to Earth exceeds the dielectric strength of the air between. When that happens, we get a discharge from the clouds to Earth in the form of a lightning bolt. This discharge results in the air along the discharge path turning into an ionized plasma form that more easily conducts charge than usual air. And as that discharge happens, a release of upwards of a gigajoule of energy can occur over a 200 millisecond interval. That's actually enough energy to power a 100-watt light bulb for almost 4 months. The susceptibility of a given geographical area to lightning is largely determined by weather patterns and local climate. There are approximately 1.4 billion flashes of lightning worldwide each year. However, those strikes are not evenly distributed on the surface of the Earth. Rather, they're concentrated over land masses in areas that experience high humidity throughout much of the year. In the US, for example, a band running from Texas through to Florida is most susceptible. The Florida area between Tampa and Orlando has the distinction of being known as Lightning Alley, with 50 strikes per square mile per year. That lightning bolt will, of course, make contact on the surface at some point, and it will take the path of least resistance. Power lines and other metallic structures, such as exposed steel pipes, are highly conductive and will make good strike points for that reason. There are three primary lightning modes that will affect a pipeline. The first is a direct strike. Here, the current flow is directed straight into the pipe at a portion above ground. It might be isolation joint, pump stations, or pigging access. This will elevate the potential of the pipe relative to its surroundings, whether it be another isolated pipe segment or the surrounding soil. If the potential difference at the pipe interface in soil exceeds the breakdown strength of the pipe coating or the isolation joints, a degradation of the material will occur, allowing the lightning energy to progress along a path to ground. Once that isolating material breaks down, the current flow then causes damage to the pipe material itself by drawing metal away, leaving a weakened or potentially perforated pipe. Pipe areas with already compromised coatings will, of course, be most susceptible to damage. This pipe and coating damage is permanent, increasing the holiday surface area on that pipe segment, which in turn changes the requirements for continued corrosion prevention by cathodic protection systems. On the isolation joints, the insulating material can be damaged, leaving shorted joints between the normally isolated pipeline segments. Once the isolation joints fail, cathodic protection systems may be impaired, allowing for continued damage to the pipe from inadequate CP. Additionally, damage to cathodic protection equipment such as rectifiers may occur. The next lightning mode is a strike to the surface soil adjacent to the pipeline. Here, a potential gradient develops from the area of the strike to surrounding areas. The pipeline segment through rectifier connections and existing coating damage will have a near ground potential. If the soil potential at the pipe interface near the lightning strike again exceeds the breakdown strength of the pipe coating, damage will occur in a manner similar to a direct strike. And again, this is permanent damage that must be addressed for continued safe operation of the pipeline. The final lightning mode involves a strike to a power line. Power lines are designed with insulators between the current conducting wires and the power pole structure. The same insulator concept is also used at step-down transformers on a distribution power line pole, and even within cathodic protection rectifiers themselves, and all have different breakdown strengths. Previously, I mentioned that lightning path from the cloud down becomes a highly conductive ionized plasma. Now, imagine when that hits a power line and its associated structure at one of those insulator points. Even after that short burst from the lightning hit, the plasma path still remains. And this plasma path can bypass those insulators that are present. With the highly conductive path present, it's now possible for the energy from the power lines to flow along the plasma path to the metallic power pole and subsequently into ground. But unlike the initial lightning strike, this current flow can be sustained for long periods of time from the energy that normally flows through the power line. And this is what's known as a flashover event. The sustained power flow can be far more damaging than the initial lightning strike due to the length of time that the current can flow. A fault condition like this is automatically terminated by power substations through briefly disconnecting the power line and then reconnecting it, but it takes time to detect that fault. Meanwhile, the energy flow through the ground again creates a potential gradient that will damage pipe coatings. Think of it like an arc welder set to maximum current with the rod striking an exposed pipe. Perforation on the pipe is a potential if the current is high enough and that flow is prolonged. This type of flashover event can also occur on pole transformers as well. This results in equipment exposure to both the energy from the initial lightning strikes as well as the high voltage present on the distribution power line. Most equipment such as rectifiers and other power supplies just aren't designed to handle the up to 35 kilovolt potential that's present on distribution power lines. This can cause significant damage to a rectifier, destroying its rectification diodes and transformer. In some cases, the energy flow may occur through the damaged equipment and into the power line itself, causing damage there as well. and also highly sensitive measurement equipment attached to the rectifier are also susceptible to this form of damage if not hardened against those types of faults. Anything to add, Sean?
That was a very thorough answer, and I don't really have much more to add to that, but I would like to say that given the damage that lightning can cause to both pipelines, CP systems, or maybe even remote monitoring systems, it's also important to keep worker safety in mind. You don't want to be anywhere near that pipeline when lightning strikes. So if you receive a weather warning, you hear or see lightning, it's critical to leave that area as quickly as possible. Also let your coworkers know that if you've detected these sort of dangers, just in case they didn't notice an incoming storm, or maybe they're even in a position where they can't see it.
Thank you both. That was a great explanation and some really valuable information. So now that we know the ways a lightning strike could affect a pipeline, could you tell me how you would evaluate the impact of a lightning strike?
Certainly, Rebecca. So evaluating the impact of lightning strike can be difficult depending on where the damage occurs. For exposed parts above ground, such as rectifiers or isolation joints, visible inspection can be performed for initial assessment. And this can be followed by field measurements to validate operation. It's usually pretty easy to see a charred rectifier as a good indicator that it's been damaged. However, for the underground elements of the pipeline, it's impossible to perform a visual inspection other than for an already failed pipe that is losing product. It's just not economically viable to dig up an entire section of pipeline to look at its entirety and its integrity. Instead, the damage can be inferred from measurement of key parameters. Changes in the amount of impressed current being delivered to a pipeline segment can indicate a change in the surface area of damaged coating. Also, potential measurements made at a test station can indicate protection criteria is no longer being met. After initial indications of damage to the pipe, more detailed studies can then be performed with, say, close interval surveys or intelligent pigging. At that point, the decision can be made to dig up affected local areas for closer inspection and remediation. Over to you, Sean.
Well, in addition to that, I'd also recommend evaluating the condition of interference or critical bonds. In the event of a very large lightning strike, it's not unusual to see the shunt damaged, or in extreme cases, the shunt can be burnt right into an open state. When that happens, not only is the bond no longer doing its job, but it may also be an indicator of potential other issues on the pipe from a lightning strike, and you'll want to look into that further as well.
Thank you both. So before we continue on with the interview, we're going to kind of change course here for a little bit. So I have a short series of questions that I'd like you to both answer. And these questions are designed to help the listeners get to know both of you a bit better. So with that said, my first question is, what's your favorite TV show, movie, podcast, book, or sport that you're consuming right now? Tony.
That's a good one. Right now, with the increased time at home from the pandemic, my standards for media consumption have unfortunately dropped significantly. So I'm shamefully watching episodes of cheesy TV shows from decades ago, like the original MacGyver.
That's great. What about you, Sean?
Well, at the moment, I'm really enjoying the Canadian podcast, The Ongoing History of New Music. It dives into the history of some historical musical events, and it's a great listen while I'm driving between distant CP sites. But of course, that's only second to the MP podcast, of course.
Oh, thank you for that. Let's see. Tony, how did you get into corrosion research?
Oh, wow, that was a few years ago. It all started with my move to Mobile Techs. To be honest, prior to that, it hadn't really been on my radar. Mobile Techs had created some custom remote monitoring products several years before I started, but had never really commercialized them into a standard offering. So after I joined, we started rolling out off-the-shelf corrosion-related equipment to multiple customers as they came to us with stories of deficiencies in existing equipment on the market. That all required learning the ins and outs of the corrosion industry, and the rest is history.
Wonderful. Sean, same question.
Well, just like many others in the corrosion industry, I kind of fell into this role. My background is in electronics, and I was working on wireless data systems at the time. Some of those systems included very early examples of cathodic protection monitors. As the demand for those CP monitors increased, so did my involvement in the industry. It was all very new to me. It was very interesting, and I was really excited to learn more. So I started taking NACE classes, I attended events, and continuously bolstering my CP knowledge. And to this day, I'm still learning about CP every day.
Great. Last question for you both. What's your biggest pet peeve, Tony?
Oh, let's see. For me, I'd say it would be dealing with third-party service providers that have inadequate support capabilities. These days, top-level service offering is often intertwined with multiple third-party service providers. And when one goes down, the final service product also has issues. The weakest link affects the reliability of the top-level service, which is what the customers see. Unfortunately, the weakness is usually on the support capabilities of the third-party lower-level services.
Okay. And what about you, Sean?
Boy, that's a really tough question. I honestly can't really think of anything, Rebecca. I really enjoy working with these people out in the field, and I get a very good sense of accomplishment when we solve difficult challenges. Nothing beats that aha moment, when you've been working on something a long time and you finally figure it out and get everything solved.
I'm glad to hear that. So I do have one final question in our interview here for you both, and that is, how can pipeline operators protect CP systems and their components from lightning strikes?
Another great question. There are two main approaches to protection against lightning, mitigation and monitoring. Now, mitigation systems are outlined quite well by NACE standard SP0177. These may include fault shields installed next to power line poles, lump grounding, gradient wires, and spark gaps. Also, solid-state decouplers, polarization cells, and solid-state overprotection devices are effective at reducing damage. These particular devices block low-voltage DC, but allow AC or high-voltage DC to flow unimpeded. Installed at isolation joints, these can protect the insulation material by reducing the potential present across the joint during lightning strike or fault condition. Installed along a pipe at strategic locations, they can also control the potential difference between the pipe and the surrounding soil during lightning strike or power line fault condition. As with lump grounding, they also allow control of AC voltages from induced sources, forming a part of an important part of an AC mitigation strategy. While adding protection against lightning and flashovers is an important countermeasure, it still won't protect against all strikes or faults. It's important to be able to detect when damage has occurred to a pipeline asset, and this is where remote monitoring comes in. Remote monitors not only allow you to monitor normal cathodic protection operation, but they also help to detect changes in the system operation. When the coating on a pipeline is damaged, an isolation joint shorted, or a rectifier system destroyed, remote monitoring units will pick up the changes in CP operational parameters on the pipeline and also the change in operation for a rectifier. For a coating deterioration, more of the pipe is exposed to soil, reducing the system resistance as seen from CP rectifiers. For a constant potential rectifier, an increase in rectifier output current will be seen. As mentioned before, at test stations, a remote monitor may observe higher instant disconnect potential near new or larger holidays in the pipe coating. A reduction in AC current densities observed at coupons may also be apparent, as increased surface areas of pipeline coating defects help reduce AC on pipelines. Also, at rectifiers, zero voltage or current output at 0 amps may indicate a completely failed impressed current system. And the need for immediate data is critical. Do you really want to continue operating a potentially compromised pipeline until the next manual survey or rectifier read? In that month or longer, significant additional damage may occur to the pipeline from lack of adequate protection. Remote monitors can convey the changes in system operation immediately when limits and alarming are utilized. Beyond the automatic data transmissions, with two-way communications equipped remote monitoring units, it's also possible to pull the units for immediate data updates after a known storm event has occurred. With the information sent to asset integrity personnel, plans for restoral of adequate CP can start immediately. The data may also support additional investigations with potential surveys or smart pigging. And in extreme cases, leaks may be detected by a more immediate site visit being triggered by remote monitoring data. To be effective, though, these remote monitoring units need to be hardened against the very source that damages the pipelines in the first place, lightning. Traditional measurement equipment tended to use grounded protection systems for inputs. Well, guess what? As mentioned before, lightning takes the path of least resistance to ground. This configuration has a tendency to result in significant damage to the equipment under severe lightning exposures. Now, newer equipment achieves lightning immunity by using the opposite approach, ground isolation where possible, and surge absorption on paths that can't be isolated. This configuration allows the lightning to take another path to ground, limiting the damage to the remote monitoring units. With this, it's possible to have surrounding equipment scorched, while the remote monitoring equipment continues to provide accurate, valuable data in the determination of that equipment's failure. Now, Sean, can you add some color with some field experiences that you've heard of?
Yeah, absolutely. So as Tony mentioned, having a robust RMU design is absolutely critical so that it can alert you when CP systems might go down due to lightning. Being on the service side of our operation, I have numerous stories about lightning damaging CP infrastructure. My favorites all follow the same general scenario. The CP tech receives an email from their RMU that the potential at a pipe or a rectifier has changed. They drive out to the site and often find obvious clues that lightning has passed through the area. Burnt up rectifier diode stacks, melted wires, open shunts, and lightning arresters that have been exploded into tiny pieces. Catastrophic damage. You can imagine their surprise when they take a look at the RMU, and despite it being covered in soot from all the surrounding damage, the LED is still on and the RMU is still running. Incredible. Over the years, we've received RMUs back from the field that are covered in this soot from nearby rectifier damage. And it's hard to believe, but all our technicians do is they just remove the electronics from the plastic RMU enclosure. They install it into a brand new plastic case. They perform some very thorough checks, and the RMU is ready to be placed back into service. The damage we find is typically just cosmetic in nature. It really speaks to the benefit of having electronics that are designed with lightning in mind. It also keeps the repair costs very low. I can still recall many years ago, we were working with a pipeline operator out of Florida, right in Lightning Alley, and he agreed to deploy an RMU in the area just to test its ability to withstand lightning, as he had a long history dealing with the damage that lightning caused his CP system. He was absolutely convinced that the RMU wouldn't even make it through one storm season, and I'm happy to report that it's been 5 years since we had that initial conversation, and that RMU is still reporting to this day. In addition to having a robust design, a two-piece design also helps make swapping out RMU components very straightforward if you do happen to suffer some collateral damage during a lightning event. It happens so infrequently that we don't even track it, but I did ask our bench tech how many RMU antennas has he received back with an electronics fault due to lightning, And he kind of scratched his head and he said, Sean, I can only think of one instance in the last 10 years. So that really speaks to how well that equipment works. If you'd like to learn more about our industry-leading Mobile-Tech's remote monitors, or if you'd like to download our white paper about lightning strikes on pipelines, please visit our website. We can be found at www.mobiltex, spelled mobiltex.com.
Thank you for sharing that. And before we go, I also wanted to mention if anybody else is listening who is interested in more information about the subject, the February issue, this month's issue of Materials Performance, has a feature article about this subject. So check that out as well. So this is where we'll end our interview today. I really want to give a big thank you to Tony DaCosta and Sean Lawrence for taking the time to join me today. Again, my name is Rebecca Bickham, editor of Materials Performance Magazine. Thanks for listening.